Alright, now I'd like to delve into our discussion about reference frames and displacement. Now, I'm just going to mention displacement very quickly and briefly here because it was extensively covered in the vector thing, the vector worksheet, the handout, as well as the video. But if you haven't seen the displacement video, I highly encourage you to check it out. And just know that this is the key takeaway here, that displacement is a vector, and it's equal to the final position vector minus the initial position vector. And that's about however much that's a very brief introduction into what displacement really is. But again, I highly encourage you to check out last week's material if you were confused about what a vector is or what displacement exactly is. But the main thing that I want to get across is about reference frames. Now, any measure of position, distance, or speed must be made with respect to a reference frame, or a frame of reference as it's often called. For example, while you are on a train traveling at 80 kilometers per hour, suppose a person, Daniel, walks past you towards the front of the train at a speed of, say, 5 kilometers per hour. So, let's say this is you, or this is Daniel, and this is the observer. So let's say Daniel is walking in that way, eastward, at 5 kilometers per hour. And let's also say that the velocity of the train is 80 kilometers per hour eastward. With respect to the person as a frame of reference, meaning that from the person's point of view, you see Daniel coming towards you at 5 kilometers per hour, and that's it. But from the perspective of, say, the ground, and let me just draw some wheels here. From the perspective of, say, the ground, Daniel is actually traveling at 85 kilometers per hour. I get the 85 from 5 plus 80. So Daniel is moving at 85 kilometers per hour with respect to the ground, but only 5 kilometers per hour with respect to you. That means that if Daniel accelerates, or if there's a problem asking about Daniel's total distance or position or some unknown quantity, it will be easier, rather than to view it from an inertial rate frame, meaning that from the point of view of the ground or from a stationary object, it might help you to view Daniel's motion as if you were there itself on the train, rather than including the train's velocity. So you can do that. There is some flexibility with that. And that's why it's very important to choose the right frame of reference, because choosing the right frame of reference can make the entire problem take 10, 20, 30, an hour less time than it might actually do. It is important to specify the frame of reference when stating a speed. In everyday life, we usually mean with respect to the Earth without even thinking about it. But the reference frame must be specified whenever there might be confusion. For example, you can't use with respect to Earth when you're dealing with interstellar objects. You will have to refer to ether or a galaxy far away, or other different problem-solving techniques if you want to, if you're stuck in that type of problem. When specifying the motion of an object, it's important to specify not only the speed, but also the direction of motion. And this is what Daniel went into a lot last week. But summing it up really quickly, velocity equals speed plus direction, where speed is the magnitudinal component and direction is the directional component needed to specify velocity. If you notice, I did not say that Daniel is traveling 5 kilometers per hour. I said he's traveling 5 kilometers per hour eastward. I didn't say that the train is moving at 80 kilometers per hour. The train is moving at 80 kilometers per hour eastward, and it is that directional component which makes all the difference. And the FEMA people, the F equals MA people, are going to try to catch you on that. Additionally, we can specify a direction by using north, east, south, and west, and by up and down. In physics, we often draw a set of coordinate axes, this Cartesian plane that we are also familiar with, To represent a frame of reference, we can always place the origin 0 and the directions of x and y, the directions of the x and y axes as we like for convenience. For example, let's say an object is falling. Let's say you have a ball and it's falling. It would, if you took this as your set of coordinate axes, with the upwards direction being positive and the downwards direction being negative, a lot of the work would be done with negative numbers, and that's just something that is one more area that you can make a mistake in. So instead of doing that, you can completely change the coordinate axes as per convenience. And if a ball is falling down, and that's the ball, let's say a ball is falling down, you don't necessarily have to make up positive and down negative. You can make down positive and up negative. It's very non-intuitive, but it's very important to realize that a lot of this is kind of subjective in physics. You get the right answer, but you may get the right answer in different frames of reference or in different coordinate axes. Objects positioned to the right of the origin of coordinates, meaning 0, on the left or to the left of the 0, have a negative, sorry, let me rephrase that. On the left of the origin is the negative numbers, and on the right of the numbers, the origin is positive numbers, but this can easily change, as I said. Any point on the plane can be specified using its x and y coordinates, but you have to be careful what is negative y, what is positive y, what is positive x, and what is negative x. I cannot emphasize this enough. A lot of problems in the F equals ma, you're going to be, the ball is going to be falling, or a rocket space shuttle is going to be diagonally falling downwards, and you need to find some unknown quantity, and taking upwards to be positive and downwards to be negative just makes you more error prone, and that doesn't always help in the context of the problem. Finally, I want to talk about position really briefly. The position of an object at any moment is given by its x coordinate if we're talking about horizontal motion, and y coordinate for vertical motion. But let's say I'm doing something on an inclined plane, which you often will. It's one of the most common types of physics problem. Let's say I'm doing something on an inclined plane. Let's say I'm standing here. I move 5 meters that way and 7 meters that way. So 5 and 7. Now, if you take this usual xy plane to be our coordinate axes, we see we have a problem, because just drawing that dotted line like that, you see that everything is diagonal. Well, what we can actually do is not just change for the coordinate axes. We don't necessarily just have to change we don't have just the power to change the signage, or which side is up, which side is down, which side is positive, which side is negative, but we also have the power to choose where we put our axis. For example, we can let this be the x-axis, and we can let this diagonal perpendicular to it be the y-axis, and we can let this be positive, this be negative. We can make this be negative, this be positive. And now when you find I walked 5 meters this way, 7 meters this way. Now when you find my total displacement, you can say it's 2 meters in the positive x direction. However, you have to make sure that when you get the results for this, you have to make sure to take this angle into account. And using SOHCAHTOA and other trigonometric identities, you have to be able to tell me in standard xy, positive x, positive y, negative x coordinate axes. You have to be able to specify how much my displacement was, and etc. Because this is what's taken for granted. This is what's taken as the set of axes whenever you submit an answer. It's just that for the sake of problem solving, you may want to use a different set of axes or different coordinates.